And today's speaker is Professor Nasir Ganikhodjaev with the talk Gibbs measures of the Potts model with finitely many spins and the limit theorems for corresponding multi-branching processes. Please, Nasir Nabil.
Thank you, Mr. Chairman. Thank you very much for including my presentation to this seminar. In this previous session, I discussed similar results for model with three spins, and respectively Kelly of third order. In this presentation, this result generalized for arbitrary finite number and also for arbitrary order of Kelly tree. So I recall you some necessary definitions. This is abstract, which one you already know. So we will use for considering for investigation of limit Gibbs measures. We firstly will construct the limit Gibbs measure. After this, corresponding Markov field, and as shown by Moore and Snell for the limit theorems for Markov measures are best studied as examples of multitype branching processes. They consider in the paper this one for the Ising model with two spins. So I will consider Potts model. This is some means generalization of Ising model on semi-infinite Kelly tree arbitrary order. So first of all, what does mean Kelly tree? Well, this usual tree of order Q, where Q greater than 1. This is infinite tree that is with countable many vertices. Graph without cyclosis, for which one is exactly Q plus 1 edges issuing from each vertex. If V is this one set of vertices and lambda is the set of edges, that so for two vertices X and Y from the set we will call nearest neighbors if there exists edge, some edge connecting them. And sometimes we will use this notation. So, and the distance between two vertices defined as number of, I can say minimal number of edges in the shortest path from X to Y. And for fixed some vertices, which one we will call maybe root, for fixed subvertices, we define these two types of sets. Wn, this is sphere of radius, n, and Vn, this is ball of the same radius. And later we will denote lambda and denote the set of edges or in Vn. This definition, x0 usually is called zeroth level vertex. Wn, all edges from Wn, this is nth level. This and the union of such and k levels from 0 to n. So now Vn, this is of course finite set, and we can consider this sequence of the sets, increasing finite sets, which one their union equal to V. That is, we can approximate later this countable set by sequence of finite subsets. So we will consider some not Kelly tree, we will consider semi-infinite Kelly tree that is the same order. That is the definition is the same, but from x0 we will assume exactly Q edges from others as before Q plus 1. In this case, this vertex x0 is called the root, and this tree grows from this root. In this case, where the cardinality of Vn equal to this number, Q power n, and cardinality of Vn equal to this usual sum of geometric progression. This picture, this semi-infinite Cayley tree of second order. So from this root, we have only two edges, from others, three, two up and one down. So now assume that at each side there is a spin which at any moment takes one of the values from this set. Because this set spin may take value from 1 to q, integer positive numbers. Since we are going to interpret the problems of statistical physics in terms of multi-type branching processes, sometimes elements the set we also will consider as a particle of type I. Note that for arbitrary vertex x, there exists q its nearest neighbors belonging wn plus 1. So for example, here, for this one, we have two nearest neighbors on wn plus 1. So the n plus 1 levels generation, this is vertexes in n plus 1 level, we can consider as generation for branching is the result of each particle at the nth level producing exactly q new particles. So for example, here this particle will produce exactly this two. So this, of course, this is not general case of branching processes, some special case where fixed the number of generated particles, which one connected with order of considering three. So, and we will consider the case when the number of new particles coincide with number of spins, that is, we have the same set. So now some definition about what is this mapping. We will call it configurations of spins of the set V. And this set is the set of all configurations. Now we'll consider Hamiltonian. That is, which one will specify to any configuration some number, real numbers, that is specify energy of each configuration. In the usual formulation, usually we're considering one parameter family of such Hamiltonians, beta h, where beta this is this number, inverse temperature, and kb this is Boltzmann constant. This beta is proportional to inverse temperature in the Kelvin scale. So now it is rather difficult problem to give complete description of all limit Gibbs measures. More or less, the satisfactory results are obtainable only for small values of beta. That is for high temperature. But situation is much more interesting in the neighborhood of infinity, that is at low temperature. So we will later see that is some main result we will have for low temperature. So now specify this model, Hamiltonian. This is a Potts model. That is, we have the spins, and for each configuration, we will specify, define its energy like this series. Here, J is some constant, maybe positive, negative. We will consider positive case. And this is a Kronecker symbol. Of course, this is infinite things, so that is we cannot operate with this Hamiltonian. So by this reason, we will introduce uh, some conditional energy. Assume so omega n, this is set of our configuration on this fixed set Vn, and let this is omega bar n fixed boundary configuration on complement of Vn. That is why fixing boundary configuration on infinite continuable path Vn this finite path. When all boundary points are fixed, as for example, as k, this boundary we will call as k's boundary. That is, we have here q different boundaries, and plus we can consider also one more free boundary. The free boundary corresponds to treating the boundary points like all other points. That is, when we're fixing boundary configuration, this conditional Hamiltonian, we will define like this one. Here, x and y belong Vn, finite path. And second term, here x in Vn, but y belong its complement. That is, I can say x belong Wn and y belong Wn plus 1, since we're considering only nearest neighbors. And of course, this is both terms, they are finite. And for free boundary, we have only this part, and this one absent, only for free boundary. So now we can define conditional Gibbs measure with this formula. So again, we have fixed this one already, boundary configuration condition. So, and for arbitrary configuration of the n, we define this conditional Gibbs measure like this ratio, where that n, this is partition function, which one is sum over all configuration on Vn. So now the limit Gibbs distribution for Hamiltonian H are constructed as infinite volume limits of conditional Gibbs distributions, infinite volume with different boundary conditions. That is, we are now fixing the n will tend to infinity, and we reach V. So now for sequence of conditional Gibbs states, we consider a problem of existing limit of such this sequence of conditional Gibbs measure. That is, we have sequence of the conditional Gibbs measure. So now problem existing limit. So for investigation this problem, we assume this omega and k. This is all configurations for which one configuration at x0 at the root equal to k. Clear, so this omega n will be equal union the sets and partition function on omega and k z and k with the same fixed boundary configuration defined like this one. So now for fixed n, we divide the partition function and the q segments, since according to this equality. And we define, since when n go to infinity, this all they are go to limit, we will consider their ratio. So we define a new variable, ukn, this is the ratio zn k to zn q. And of course, when k equal q, we have 1. That is k here run spins without q. So now we can produce these recurrent equations. So this is partition function zkn plus 1 that is defined on Vn plus 1. This is which one was defined on Vn. And this value, this partition function, we can express, find like this equality. Here Q is order of our Kelly tree. So now theta here exponent beta g, and since g positive, theta positive. So according to this one, UKN plus 1 will be equal to this ratio. And if limit UK exists, then we consider system with its fixed points of this nonlinear equations. It is evident that UK equal to 1, this is solution. And we can also verify, so for some indexes, for some spins, these equations will have equality, ui, for example, equal to uj. So now we can investigate all limits. Let AS, this is subset of this set, that is all spins without Q, and assume coordinate of S equal to S, and S run from 0 to Q minus 1. Then for this, our first result. So for this system of equation, there exists at least two power q minus 1 solutions. That is, we can find 2 power q minus 1 different limit Gibbs measures. This is solution, of course, they are all these measures, they are translation invariant. Here proof, this is for a for given subset AS, measure assume so UI equal to 1, and for others assume so UG will be X, that is the same for all J. For S equal to Q1, we have so all UI equal to 1, and we have this measure mu0 such that, so for one-dimensional cylinder sets, this measure specified like uniform distribution. So now for others measures, when S between less than Q minus 2, then we have this equality. This is from these equations. So we can show, so for this case, exists this critical value of parameter, which one depends from S, such that for theta greater than 1, the equation has exactly two roots, and with these two roots, they are different than 1. So for AS, we have for each equation has two solutions, and for S equal to minus 1 was already shown there exists a uniform distribution. Thus, totally exists so much solutions. And finally, this answer. So their number 2 power q minus 1. So now we can investigate, find this exit value of these two roots. For this one, consider this function. Its first derivative equal to this value, where A and B, they are denoted like here. And for second derivative, we have, and this point, inflection point, we consider this function when x is positive. So now, since this value positive, we have so our function increasing, convex when x less than inflection point, and concave when x greater. And for any s, the function, this one satisfies these three conditions. So from this condition follows, so we have one root less than one, and second root, this is which one corresponds free boundary. Third root, when x inflection greater than one, third root equal to one. And here we are verifying when inflection greater than one. Solving this equation, we have this solution. So we have the sequence of critical parameters that this one for s equals 0, for s 1, 2, till q minus 1. So the theorem, sketch of the theorem done. So since all other roots they has very complex structure, in this presentation I will consider only this limit Gibbs measure this free boundary that is uniform distribution. Other one also we can investigate, but this is a very huge calculations. So here shown how we can computing one-dimensional cylinder set, measure of one-dimensional cylinder sets for each measure. So now we can define measure of Q plus one-dimensional cylinder sets. That is root, and this is all points on W1. And here this partition function, such conditions, this is denoted notationally. So for configuration this one on W1, let K1 is the number of spins 1, K2 is number of spins 2, and so on, and KQ is the number of spins Q, where their sum equal to Q. Because we not generated exactly Q particles. So then there exists exactly this different configurations. This number of different configurations on W1 with such boundary, with fixed key, and since some key is equal to Q, then they exist such number non-negative integer solutions. So by this reason we can compute Z and K as the sum. Yeah. And Zn plus 1 can be produced find as like this equality formula. And we can compute conditional Gibbs measure for Q plus 1 dimensional cylinder set, this one, with free boundary, or their ratio. So now substituting we can show, so by fixing here all spins, except here only here J, here I. Then their ratio equal to this ratio that is equal to 1 over T10. And respectively, we can find transition probabilities, their ratio equal to the same 1 over theta. So we produce this Markov chain of Markov random field with such transition probabilities, and transition matrix has such form that is B-stochastic matrix. And for the B-stochastic matrix, similarly, we can construct other Markov measures for other roots, but here I will consider limit ourselves to only mu zero because more easy calculate more simple calculations. So now Hamiltonian of the pots, since Hamiltonian of the pots model is defined by Kroneker's delta, then the limit Gibbs measure depend only on the cardinality of this set of spins. So by the reason we will instead of until Q consider such spins on integers. F tilde, this is from minus m till m, where if Q equal to m plus 1, and such pi without 0 if Q equal to m's. Then we can define family of random variables using this such way. This is coordinate functions, where now value omega x belong f tilde. That is maybe negative, maybe positive. So note that this family of random variables one can consider as triangular array, scheme of series of random variables sigma x with xn, this is sum, where n this one. So now it is easier to show, so expectation for respect to mu measure mu zero of this random variable equal to 0. In this patient, equal to if Q even this value, if Q odd this value. So, as noted above, the elements of F tilde we will also consider as particles of type I, or maybe as AI. So now assume so each particle that is now consider multi-type branching process. Assume that each particle produces for next generation exactly 2 m plus 1 particles. And if it is of either type, it can produce for the next generation particles of all 2m plus 1 types. This is our particles, their type from this one to this one. So now for arbitrary k, assume p a k this one. This is probability that a particle of type ak produce such number of particles minus m, this one, such number of particles of this one, and so on. This now am last one is particles, the number of particles of type am. So then this probability we can compute using previous transition probability like this one. And if let xn, this is be a random vector with where xin, the number of particles type I after n generation. The behavior of branching process depends on the expected number of each type of particle produced by a given type. And the behavior of this process depends on expected number. It's repeated two times. So now we can compute these expectations. So if let M is matrix of this such enters, then easy to show. So this M will be equal to this value, 2M plus 1 product to PKL. That is, we have, so our new matrix will be equal to 2M plus 1 times our previous transition probability matrix. So now the largest value, since pi is bistochastic, the largest eigenvalue of this matrix, so largest eigenvalue equal to 2A plus 1 with multiplicity 1. And with eigenvectors, this is multiplication from left, this is multiplication from right. So we have, so W, since pi is double stochastic matrix, W has such form. And second one, this vector V is all coordinates equal to 1. So now this is basic limit theorem from this book. For example, for branching states that this is a vector over this number converges with probability 1 to a limiting vector which has direction W. And this theorem requires some additional condition, which one already we have checked well. So the number of particles produced by single particles, for example, this number is sufficient to assume that variance of this distribution be finite. Already this was shown above. So this proof, we can find this proof. So in this case, theorem, the second one. So this sum equal to exactly Wn because according to our conditions, this Wn the number of vertices on Wn's level. So then for particle of type I, this ratio x1 will converge with probability 1 to this constant 1 over 2m plus 1. And here interesting result about Kesten Stigium. They proved additional limit theorems for multi-type branching processes. They proved the limit theorem for random variables of the form Zn, this is our previous vector. Zn, this is new random variables, which has form xn product to scalar product to vector A, where A is a vector orthogonal to W. So in our case, we can find m plus 1 such number of vectors which are orthogonal to W, for which m coordinates equal to 1, one coordinate 0, and others equal to minus 1. And for them, we can formulate, they showed that the form of the limit allow for that n depends the eigenvalues of m, which has second largest model. That is, we should now verify second by modulo second largest eigenvalues. So in our case, the second largest eigenvalue equal to this number. And this one condition was so square should be less than the first eigenvalue. This is we are verifying. So this is lambda 2 square. This is lambda 1. And we will have this inequality for theta showing less than this value. And so, for example, we can, as A, consider this vector. And we will have, so that n equal to the sum of all positive minus sum of all negatives. In this case, according Kasten-Stigin additional limit theorem, we will have if theta less than this value, then this Zn over this is constant, converge in distribution to normal random variable with mean 0 and variance sigma square with this value. So now one more application of this theorem. Kasten-Stigin theorem. They prove so if lambda 2 square less than lambda 1, the same reduced condition. So then our Gibbs measure will be extremal. So it is known, so for example, that the set of Gibbs states with Hamiltonian H is non-empty, compact, convex subsets of the set of all probability measures PH on omega. So GH is Gibbs measures, PH all probability measures, and GH is non-empty, compact, convex subset. So limit Gibbs measure is an extreme point of the set if there does not exist two different measures, Gibbs measures, for which one mu is average, mu1, mu2. Then using a Kasten-Stigin additional limit theorem, we can state that so if this is critical temperature, and if temperature greater than this value, then measure mu the measure is extremal. So here, this temperature Tcm is decreasing with respect to argument m. Increasing m, this temperature also will increase. But for temperature less than this one, this measure already is not extremal. That is maybe defined as average, convex average of two different measures. So here, of course, a lot of problems, but here I consider only simple case for mu0, that is limit Gibbs measure free boundary configurations. The same result we can prove, but in this case, calculation will be rather very, very complete. But main idea is the same. Okay, that is all from me. Thank you for your attention.
Thank you very much for interesting talk. Maybe someone have questions or comments, please. I have a question relatively to the construction of the branching process. It is related to the structure of Kelly tree, which you
Yeah.
can see. So what about the general branching process when we can have a lot of descents and different number? Can it be related to also to some construction of Gibbs measure with spins at every point?
So here, really, this particular case when the number of generated particles fixed, and this is equal to uh, order of our considered tree.
Mhm.
This is mm, this is for when I have found one paper when for Ising model was this model studying of limit Gibbs measure for Ising model, some more deep things, magnetization, something like this one, was connected with multi-type branching processes, only with two types. And they, these others already I mentioned, they consider exactly Ising model only Ising model with two spins on the semi-infinite Kelly tree. For general case, no, first of all, only after reading this paper, I did start a little bit study this multi-type branching processes. So now this is my first result, because usually, as you remember, for me more interesting was models of statistical physics, some
Mhm.
competing interaction or something like this one. But and since I am working in stochastic department, and this was bridge from my considerations to branching processes. And this is only my first result. And other one, this much better know, for example, Sadullah or my colleagues, which
I see.
they are specialists. This is my first experiment for branching processes. For me, it was interesting only how uh, this is how we can apply casting student results for models of statistical physics. And what last result really this is very interesting, but maybe I explain it a little very shortly. So one of the interesting problem when considered measure is extremal.
Mhm.
In this Kasten theorem, additional limit theorem, give answer also for this question. So, and really, for low temperature, our measure will be extremal.
Mhm.
Non-extremal. For mu zero, I mean. For high temperature, this is extremal. So this is my answer because this is my first, second, because in previous I consider model with three spins. So now general case. So this one.
Okay, thank you. And also, I have another question. You more or less easily get the recurrent equation for for statistical sum. Yes.
Yeah.
Yeah. But can we do the same for some other characteristic like total energy or something related to our measures on the finite subsets?
No, of course, this everything we can done. For example, this interesting question, but we not consider today. So, but is connected with physics. some magnetization. Then we have magnetization. When we have paramagnetic, something was interesting problem connected to physics, coming from physics, and full partition functions. Of course, this very effective instrument for only in this case, because for Kelly tree, this is tree we here don't have cycles, so we can produce recurrent equations.
Yes, yes.
For example, the same model on ZD, the tree needs to more difficult, more deep. So another approach.
I see. Okay. Thank you very much again. And if there are no another questions or comments, then for today this is finish of our job. Maybe Georgi, do you know who will be next speaker?
Next speaker will be Vitaly Konarovsky.
Okay, good. So see you next week. For today, that's all. Bye.
Okay, bye.
Bye.